Oh, you can't see. Let's see, how many lessons have we got left to do? Okay, we're okay. We've got 1, 2, 3, 4, 5, 6, 7 hours left to teach. 2 today. 2, 4. I should be try to be finished next week. Hope. Right, can you see?
Yes.
Okay, let's get started. If you want to write that down.
Yeah.
Oh, you have it already. Good. Okay, start.
Yeah.
So, a few little things to look at here. So look at the following circuit. Quite simple. So what you have here is a cell, and here you have 2 plates, conductive plates. Don't worry about this material, it's not so important for us right now. And this will be a positive and this is a negative, and what will happen is this plate will become positively charged and this plate will become negatively charged. And what's very, very interesting is if you turn this off, so it's gone, the charge here and here will then start to flow for a short time. So what you can do, I can show you here with this, you can take like 2 pieces of metal and you put them really close to each other, but don't touch, okay? And then you pass a current, and current comes out here. This will become positive and this will become negative. Then if you turn the current off, it will continue to flow for a short time, because what you've done is you've captured and stored some of the current in this. Yeah. So, okay, that's what I'm just saying there. So this is actually what we call the capacitor, and the symbol is this symbol. And you see how it's similar to this symbol? Because it does something similar. It releases a charge. But the big difference is it only releases a small charge. It stores it for a small time. Do you understand? Yeah? Have you seen these before?
Yes.
Yeah? You've seen this before?
Maybe
Okay. So the definition is a capacitor, it's also called a condenser, but that's an old term for it. You don't need to write that down. A capacitor is an electronic device that stores electrical energy. So what the capacitor does. Oh, and also you should also write down this symbol here for the capacitor, this capacitor symbol. Continue? Yeah? Okay. So, now we'll need a way to measure capacitors, because some capacitors can hold a lot of charge and some will hold a little charge. So capacitance is what we call the ability to store charge in a capacitor. And the unit we use is called farad. Yeah, you've heard of this before? So, as a definition, the capacitance is defined as the charge that can be held by the capacitor divided by the voltage. Yeah? So, you can see that if it can hold, wait one sec, if it can hold a lot of charge, we say it has a big C.
Yeah.
And if it can do this with a small voltage, we say it's a big C. Okay, so now you can write that much down. C is capacitance, Q is charge, and V is voltage. Do you have a busy day today? What time do you start at?
10.
That's okay.
I find to be a bit fast.
Yeah?
Maybe because of the first day of the week. For
Yeah,
study.
I think perhaps so.
So C is farad.
You measure in farads, yeah. So I'll say what a farad is now in a moment.
A unit.
It's a unit, yeah.
Okay.
So, a farad, well, you can probably guess what a farad is. So we measure C in farads, yeah? And Q, what do we measure Q in? What unit is for Q?
Ham.
Q is charge.
Charge.
Yeah.
C.
Yeah, what's that called? Ah, come on, what's its name?
I forgot.
Oh, Ben. Khalifa, do you remember what C is called? No? Coulomb.
Oh, Coulomb.
Yeah, come on. And what do you measure V in? Volts.
Yeah.
Right, so what do you think a farad is? What do you think a farad is? Yeah? Yeah, no, but looking at this formula, what could you say 1 farad is? Now what's this? What do we say this one is? Coulomb. And this one? And this one? Farad.
Coulomb.
So a farad is,
1
yeah?
Coulomb
Yeah.
over volt.
Yeah, so how do we say that? We say a farad is 1 coulomb of charge per volt. That is, a farad is the same as a coulomb per volt. Yeah? I was talking today to Colin about how difficult it is for my engineering students to remember words. So difficult.
So, Coulomb say.
What did Colin say? Let's see. What did he say?
No way.
He said he was Colin was angry.
Oh.
And this includes you too, Khalifa, because you forgot that C stands for Coulomb. It's not just the Chinese kids, it's you too. Okay. Try to remember. Yeah. Continue.
Okay.
Now, here is an example of a capacitor. Now it's an old example, I know, but it gives you the idea. What happens here is, well, maybe you don't have any experience of this, but I remember anyways with the old cameras, you press a button and then you have to wait.
So like 3 seconds.
No longer than 3 seconds for these ones, yeah, like 30 seconds. Yeah. So what happens is there's a capacitor and the charge builds up. And then when there's enough charge, is released.
Capture.
Yeah, yeah. So it's an example of using a capacitor. And the capacitor, it builds up the charge gets bigger, and then you press the button and you release the charge and you get a flash. A lot of energy. Okay. This is an example of how you could use a capacitor. Now, it's not necessary anymore because on your iPhones and things like this, you have special circuits that will make the high voltage very quickly. So it's not necessary anymore. Can you think of anything else that uses a capacitor?
Printer.
No, because there's no need to wait. I don't think so. You need to think of something electrical where you have to wait.
Heater? Boiling heat?
No, because when you turn the heater on, it produces heat instantly. You need to think of something where you have to wait before you can use it. And also, it produces a lot of voltage.
See, wait.
Yeah, what's this?
Whoa, wait.
No?
Yes.
Can you think of anything? Yeah?
EVS.
What's that?
Like it's something, the thing that you place in the wall, on it, let it charge before it shows the green light for you to put your, it's like an adapter, but the one that reads
How long do you have to wait?
like a minute.
Okay, perhaps so. I've not seen these before. But if you have to wait a minute, that sounds like a capacitor.
Yes.
Yeah.
When you take the light, like for example, there's no current, it will keep on charging your phone till that minute, then it will die.
Right, so there's a capacitor that has to charge up for 1 minute. Okay, I can see that, yeah. I'll give you an example which I think you both know though. I'm sure you know what this is.
Yes.
You know?
The
Yes.
heart rate.
Yeah, for heart attacks. This is a good example of capacitor. Because actually, you can hear it charging up. Yeah, that sound is the capacitor charging up. So you can hear it. So this is an example of capacitor. Now, here's a simple little question for you to do. You have the formula. So I want, if the capacitance is 1500 microfarads, and if the voltage is 380, I want you to calculate the charge, the Q.
The color.
Yeah. Question, Ben? It's okay?
Okay.
Yeah.
But it was 1 point. Is this going to be low? Like very low?
No.
Very high.
0.57.
I got 1.875.
What did you type in?
The farad
Yeah.
over.
Over? No.
No, farad. Sorry, column equals to farad times. Times 380.
Ah, you're confusing me.
No, sorry, it's 380.
It's like this, isn't it? C equals Q over V, so Q equals CV.
Yeah.
And the C was 1500 times 10 to the minus 6, and the V is 380.
Yeah.
So what did you get, Ben?
0.57.
Coulombs. Yeah? Yeah? That's 570 millicoulombs.
Yeah.
Okay, is that okay? That's easy enough to get started, right? Right. Let's continue. So we have some rules when it comes to combining capacitors. So the first one is if they're parallel. And we would like to replace it with one capacitor. Like this. Yeah? Yeah, is this okay? So let's try and figure out the formula together. Let's say that's C1 and that's C2. And this is C. And we want to know what it is. Maybe it's C1 plus C2. Or maybe it's something else. Okay? Now look. Let's say this guy here has Q1 and this one here has Q2. What happens when the Q's come out? You get Q1 plus Q2 because the charge adds. So that means this one here has Q1 plus Q2. It's supposed to be the same. Okay. Now, what's the voltage here? Let's say it's just V. This voltage, is it the same or different?
Same.
Same. And this voltage?
Zero.
Same. So that means this one has to be the same then. So you know that C equals Q over V. That's equal to Q1 plus Q2 over V. That's Q1 over V plus Q2 over V.
Yeah.
What's Q1 over V? That's C1.
Yeah.
And Q2 over V?
C2.
C2. So in other words, our first form, you don't need to write this proof down. Our first formula is that C equals C1 plus C2 if they're in parallel. And I say remember that the voltage is the same and the charges add. Now most electrical devices actually have a small capacitor inside. Most do. And the reason for this is it helps control the fluctuations. You know, so if you suddenly have slightly too much current, then the capacitor can absorb it. I was saying to Khalifa that most electrical devices, laptop, TV, phone, they have small capacitors inside them. And the reason is if the current suddenly increases slightly, then the capacitor can take the extra charge. And if the current suddenly drops slightly, then it can release the extra charge. So capacitors can help smooth the current. Smooth out the current. Yeah, that's so important. Now the next one, of course, we have to do is series. So let's see if we can find out the formula here for series. So you have, now you could probably guess what the formula is, but let's see if we can prove it. Yeah? I know, don't write it down yet. Let's try to prove it. So we have one capacitor here,
Yeah.
and one capacitor here,
Yeah.
and we want to replace it with one capacitor here, like that. Okay, so let's figure it out. This is Q1, and this is Q2. And we learned earlier that they're equal. Yeah, that the current has to be the same.
Yeah.
So if you were to watch the current move here and here, it has to be the same amount of current.
Yeah.
Yeah, because we learned this when we look at the simple circuits. So they're the same. Okay. So that means that this guy here is the same as well. They're all the same. Okay, so this one has a voltage, V1, and this one has a voltage, V2. And we learned in simple circuits, this one has a voltage, what would it be?
V1,
Plus V2. Yeah. So C is Q over V1 plus V2. So then that means C over Q is 1 over V1 plus V2. Okay? Because I just bring the Q down here. Okay? So that means Q over C hang on, I forgot what I'm trying to get to. Oh, I want to simplify this. Okay, so let me just go back here. So I can say C1 is Q over V1 and C2 is Q over V2. So that means V1 is C1Q and V2 is C2Q. Okay, let me put them in here. So that's Q over C1Q, C2Q. So that's 1 over C1 plus C2. So that means 1 over C equals C1 plus C2.
Yeah.
Something went wrong here. Something went wrong.
Huh?
Yeah.
Okay.
Yeah, I think something went wrong here. Something went very wrong. Hang on.
Yeah. C2 equal C1 equals Q per V1.
Yeah.
And V1 equal Q per C1.
Here.
Yeah.
Disgraceful. Thank you, Ben. V1 equals Q over C1 and V2 equals Q over C2. That's better. So that means C equals Q over C1 plus Q over C2.
Yeah.
Cancel. 1 over C1 plus 1 over C2. That's C. So that means 1 over C is 1 over C1 plus 1 over C2. There we go. Sorry. Thank you, Ben. So we have our second rule, which you could have guessed. Remember, voltage is different in adds and the charge is constant. You have that, Kalisa?
Yes.
Yeah? Problems?
Oh.
It's Gal. What does she want?
She want to know, isn't we talk about some essay?
No, it can just be physics. You want to reply to her? Tell her only physics today.
Tell her to watch the video.
That too. Yeah. Right. A 100 millifarad capacitor is connected to 200 millifarad. These are connected using a 10 volt battery. They're connected in parallel. First, draw the circuit. Okay, so in parallel they look like this. Like that. Like that. And then what I've done is I've put, this is 10 volts. This is 100 millifarad, and this is 200 millifarad. So that's a 300 millifarad. So my first question is draw it. Did you all copy that?
Yes.
Yeah, you have that?
Yeah.
Yeah. So I want you guys to try the next part. Well, you've already done the next part. What is the total capacitance? That's, Khalifa, you just said it a moment ago. What's the total capacitance?
300.
300. Okay, my next question for you to do is what's the charge on each capacitor?
Pardon?
What is the charge on each capacitor?
Charge is Q.
Yes. And what unit is Q?
Coulomb.
Coulombs. Not column, he's your teacher. Yeah.
Coulomb.
Coulomb, yes.
I know Coulomb.
Yeah, you have column, Connell, Coulomb. All different.
What?
Connell,
Cano?
he's an English teacher.
Oh.
Connell, column, Coulomb.
I know column
You know column.
and con.
And who else?
Con.
Con?
C-O-L-M.
Column.
Con.
Column. Yeah.
Okay. Both is 10. Okay. But it's different. Oh, it's the same. Yeah, the same.
What's the same?
Whoa. Whoa. T.
Yeah, it's the same for both. They're both 10.
So you want each, okay.
Yeah.
100 for one coulomb. 2 coulomb.
1 and 2, is it?
Yeah. And 4 is
Good.
2.
Okay. What is the total charge?
Oh, it's 3.
It's 3, yeah. Because you have 1 and 2 and they combine and they'll make 3. Okay. And the last one, what's the voltage on each capacitor? 10.
Yeah,
10 and 10.
10. Yeah.
Yeah, easy peasy, right? Okay. Which?
On each, okay.
Right, now let's do the next part. So, can you draw them? Is that Gail, what she say?
Yeah, she say.
She'll watch the video?
You didn't ask something for essay?
No,
I should tell her.
We'll do it next class.
Okay.
Yeah.
There's no one is here.
Yeah, I'd like everyone here.
Please, can you go back to drawing?
Yeah.
The exam, are you going to access the draw?
Ah, yeah, they could. Yeah?
Also, next question is.
Yeah, so then now put them in series.
Oh. It can go. No. Okay, battery. So. Pardon.
So what's the total capacitance? So that formula, what formula do you need? 1 over C.
Yeah, 1 over C. So it's 3 per 2. No. Wait.
Let's see, it's 1 over 0.1 plus 1 over 0.2. That's 3 over 0.2, 0.2 over 3, 1
3.
over 6.
So C equals 2.
1 over 15? Let's calculate it. 1 over C equals 1 over 0.1.
Plus 1 over 0.2. Equals to 3 over 0.3.
0.2. Yeah, I think so. So that means C is 0.2 over 3, which is 1 over 15.
Oh yeah.
1 over 15 farads.
Yeah.
Sorry, am I not going to add 0.1 plus 0.2 to give you 0.3?
No.
Okay. In case maybe 0.2 and 0.3, the answer is 3 over 0.3.
No. Type this in and you can see. So, it's like this, Khalifa. If you add 2 like this, the answer is this. Khalifa? It's like this.
Yes.
Okay, what's the next one? What's the charge on each capacitor?
0.1 and 0.2.
No, that's the capacitance. I want the Q.
The Q.
Yeah, on each. So they're like this now.
It's constant. So, hold on.
And we said that's the same as one of these. 0.1 farads, 0.2 farads, 1 over 15 farads. I want the Q. I want Q1. Well look, Q1 is the same as Q2. And that's the same as Q. And the voltage is 10.
Yeah.
So if you have
10.
C equals Q over V, then Q equals CV, which will be 1.5 coulombs. So they both have 1.5 coulombs.
1.5.
Yeah?
1 over.
Oh, sorry. 0.67
Oh yeah.
coulombs.
Yeah.
I had it upside down.
Oh yeah.
Okay. Now, next. What is the total charge? Also 0.67. Finally, what is the voltage on each? Okay, so this voltage here will be V1.
Yeah.
This voltage here will be V2. And all we know is that the total
10.
must be 10. But we can use this formula again. So we can say V1 is Q1 over C1.
We know C.
Which is 0.67 over 0.1.
We know Q and C.
Yeah, so it'll be about 6.67 volts. And then V2 will be 3.33 volts. Okay. Okay, you wrote that down? You have what you need? So it's like the resistors last week, isn't it? You add the 2 resistors. You know, because last week we had, what did we have? We had 1 over R equals 1 over R1 plus 1 over R2. But that is when they were like this. And then for capacitors, which are like this, it's different. It's C equals C1 plus C2. And then when resistors are like this, it's R equals R1 plus R2. And the capacitors, when they're like this, it's 1 over C equals 1 over C1 plus 1 over C2. So don't mix them, please. Be careful. Yeah? Here, when we did resistors, we had the VIR and we had the VIR. And today, for the capacitors, we have C equals Q over V. C equals Q over V.
CV.
Yeah, what would be the formula? QCV. Yeah. That's right, Ben. So C is Q over V. V is Q over C. QCV. Yeah, nice. So there's similarities between the 2 lessons. QCV, I like it. Okay. So just that example.
Finish.
No, come on, Ben. What have we got here? We've got, and we still have to do this today.
Okay.
We've got lots. What's the time? just do a couple of these now.
Okay.
We'll start the next lesson.
Okay.